Okay, now we've got to talk about free energy relationships. If a reaction can be expressed as a series of reactions, the sum of the delta G values of these individual reactions is the delta G of the total reaction. And that's a consequence of delta G being a state function. If a reaction is reversed, the sign of its delta G value reverses. And if the amounts of materials are multiplied by a factor, the value of the delta G is multiplied by the same factor. In other words, the value of delta G of a reaction is extensive. Now write out the mass action equation for N2O4 as a gas in equilibrium with 2NO2 as a gas. So now we're going to look at some relationships between Q, KEQ, and delta G. First of all, if Q is less than KEQ, is the reaction at equilibrium? If not, in which direction must the system shift to reach equilibrium? In this situation, is Q divided by K less than, greater than, or equal to 1? And if that's true, then is the natural log of Q over K less than, greater than, or equal to 0? And for this situation, is delta G less than, greater than, or equal to 0? Turn your playback off, think about these questions, and then come back and we will discuss them. All right, here we go. So Q is less than KEQ. That means that the numerator is too small, that's the product side, and the denominator is too large, that's the reagent side. So the system has to shift toward the products to reach equilibrium. That will increase the value of Q until it does equal KEQ. So now think about this. Is Q over K less than, greater than, or equal to 1? Well, we've already determined that Q is less than K, and if Q is less than K, then the ratio of Q divided by K has to be less than 1. It's going to be a decimal, right? If the numerator is smaller than the denominator. All right, so we know Q over K is going to be less than 1, and if that's true, is the natural log of Q divided by K less than, greater than, or equal to 0? So let's take the natural logarithm of a number less than 1, maybe 0.5, natural logarithm. Here it is. As a decimal, it is a negative natural logarithm, and it's going to be less than 0. It's going to be a negative value, the natural log of Q divided by K. So we have determined that the reaction is spontaneous toward the product side. And we know for a spontaneous change from reagent to product that the delta G for the reaction is negative. So we know that delta G here is less than 0. Now, the third issue here is what happens if Q is greater than KEQ, and there everything we've just talked about is kind of reversed. With Q greater than KEQ, that means the numerator is larger than it should be. You have too much product, and the reaction has to go toward the reagent side to make Q smaller until it equals KEQ, and then you're at equilibrium. So Q divided by K in this situation is going to be greater than 1. And if that's true, is the natural log of Q divided by K less than, greater than, or equal to 0? And take the natural logarithm of 5, a number greater than 1. This is a positive number. Natural log is going to be greater than 0. It's going to be here a positive value, the natural log of Q over K. Here we have determined that the reaction is non-spontaneous toward the product side. And we know for a non-spontaneous change from reagent to product that the delta G for the reaction is positive. Therefore, the delta G for this reaction is greater than 0. And finally, at equilibrium, if Q equals K, then Q divided by K equals 1. The natural log of Q divided by K equals 0. And at equilibrium, delta G is equal to 0. So from these relationships between Q and K, one can derive that delta G equals delta G0 plus RT ln Q, where R equals 0.00831 kilojoules per mole K, and temperature, absolute temperature, equals 298. Now, delta G0 is the free energy under standard conditions. All concentrations are at 1 molar or 1 atmosphere. So Q is equal to 1. Therefore, delta G equals delta G0, but only under these standard conditions. At equilibrium, delta G equals 0 and Q is equal to K. Delta G0 equals minus RT ln K. This is a formula that links the equilibrium constant with the free energy under standard conditions. So if delta G0 is plus 25, in that case, and you can work this out, KEQ would have to be 4.12 times 10 to the minus 5 from this equation here. And it means that if all concentrations were at 1 molar, then you would not be at equilibrium. It would have to shift to the left, concentration of reagents increasing and the concentration of products decreasing until delta G equals 0. Then you are at equilibrium. It's easy to do, but don't do it. Don't confuse delta G, which is the free energy under any conditions, with delta G0. It's only under standard conditions that delta G will equal delta G0. So just to review, delta G under non-standard conditions, delta G equals delta G0 only when the reactants and products are in their standard states. That's what that little 0 means, that the reagents and products are in their standard states. And that means their normal state or phase at that temperature. And if you're talking about a gas, the partial pressure of the gas will be 1 atmosphere. And if you're talking about a solution, the concentration of the solution will be 1 molar. Now, under non-standard conditions, delta G equals delta G0 plus RT ln Q, where Q is the reaction quotient. Now, at equilibrium, delta G equals 0. So you can rearrange this equation if you bring plus RT ln Q to the other side. Remember, delta G is now 0. You will have delta G0 equals minus RT ln K, the equilibrium constant. So you now have an equation that links the delta G at standard conditions to the equilibrium constant of the reaction. Delta G0 equals minus RT ln K. Now, just to help you visualize what happens here with these equations, suppose we have liquid water in equilibrium with water vapor. The Q for this process is going to be simply the partial pressure of the water vapor pressure. Yes, it's products over reagents, but the reagent is pure liquid water, so it doesn't appear in the mass action equation, remember? So it's just Q equals the partial pressure of water vapor. Now, let's start at this side where we have pure water and almost no water vapor. The partial pressure of the water vapor is 1 times 10 to the minus 50 atmospheres. So like I said, practically no water vapor. If we were to plug in Q in this equation here, and you can do this, we won't do it on the screen here, but you can do this. It's simply going to be 2.5 times the natural log of 1 times 10 to the minus 50. You will have a very negative number. Delta G will be negative, so the reaction will proceed toward the product side, toward water vapor. On the other extreme, suppose the partial pressure of the water vapor is 1 atmosphere. In other words, Q equals 1. If you plug that in, delta G of the reaction would equal 8.59 plus 8.59. This term would be 0, right? The natural log of 1 would be 0. So this term doesn't exist. So that is a very positive delta G, which means that the reaction shifts from the products to the reagents, and down it would go. Finally, at some point you would get to equilibrium where the partial pressure of water at this temperature is 3.13 times 10 to the minus 2 atmospheres. Now if we plug that in as Q here in our equation, this term will just about equal 8.59 kilojoules, and delta G will equal 0. In other words, you've attained equilibrium. Well, here's an example of a delta G calculation. Calculate the delta G at 427 degrees Celsius for the reaction below, and the reaction below is nitrogen plus 3 hydrogens in equilibrium with 2 moles of ammonia, NH3. If the partial pressure of the nitrogen is 33 atmospheres, the partial pressure of the hydrogen gas is 99 atmospheres, and the partial pressure of the ammonia is 2 atmospheres. So how would you do this? So the first step in doing this is to calculate the delta G0 for this reaction at 427 degrees Celsius. And you're going to calculate it in joules. So these answers are all in joules. How would you go about doing that? Turn your playback off, try it, and come back. We'll discuss it. Okay, here we go. First you would use the free energy equation. Delta G under standard conditions equals the change in enthalpy at standard conditions minus the absolute temperature times the change in entropy at standard conditions. So all these data are given to you up in the problem. You know that the change in enthalpy for the reaction is going to be minus 46.19 kilojoules per mole. Of course, with nitrogen and hydrogen being in their stable elemental form, their enthalpy is going to be 0. So pretty much you're handed the enthalpy of the reaction by being given the enthalpy of the formation of ammonia. And the delta S for the entire reaction is minus 198.2 joules per Kelvin. So the question wants you to calculate this in terms of joules, but I've gone ahead and calculated it in terms of kilojoules and then switched that over to joules. So delta G0 equals delta H0 minus T delta S, the free energy equation. We're going to multiply 2 because we have 2 moles of ammonia times minus 46.19 kilojoules per mole as the heat of the reaction, minus the absolute temperature, which is going to be 427 plus 273, that'll be the absolute temperature in Kelvin, times the delta S for the entire reaction in kilojoules is minus 0.1982. So working that through, we get 46.36 kilojoules, which is 46,400 joules. So that's going to be answer B. Okay, let's do the second half of this problem now. Calculate the delta G. That's the free energy under non-standard conditions at 427 degrees Celsius for the reaction that we just looked at. Nitrogen plus 3 hydrogen yields 2 ammonia. And we just calculated the free energy under standard conditions for this reaction as 46,400 joules. So now what do? How do we calculate delta G? And we're going to use this equation. Delta G under non-standard conditions, that's why the little 0 is not there, equals the delta G under standard conditions plus RT ln Q. So here's the first step, is to figure out what Q is. And of course Q is the value of the mass action equation, products divided by reagents to the power of the moles of the balanced equation. So our first step, can you calculate Q? Turn your playback off, try it, and come back, we'll discuss it. So here it is. It's the partial pressure of the ammonia squared, because we have 2 moles of the ammonia, divided by the partial pressure of the nitrogen times the partial pressure of the hydrogen gas cubed, because there are 3 moles of it. So we calculate that by plugging in the partial pressures, and we get 1.2 times 10 to the minus 7. That's Q. So you're going to use Q in this equation to calculate the delta G under these non-standard conditions. It would help probably if we gave you R. R is 8.314 joules per Kelvin, and the absolute temperature in Kelvin is degrees Celsius plus 273. And you already calculated delta G0 from the last question, 46,400 joules. So turn your playback off, see if you can calculate it. So delta G under these non-standard conditions is 46,400 joules, that's delta G0, plus 8.314 joules per Kelvin, multiplied by 700 Kelvin, multiplied by the natural log of 1.2 times 10 to the minus 7. So your answer should be minus 46,300 joules or minus 46 kilojoules. So here's another example of how we can use free energy. We're going to calculate the equilibrium constant for a reaction, exactly the one that we're just looking at, from the enthalpy of the reaction under standard conditions and the entropy of the reaction under standard conditions. So there's the question. Estimate the equilibrium constant and position of equilibrium for the following reaction. And it's the one we just looked at. Nitrogen plus 3 hydrogen yields 2 ammonia. So just like we did before, this is just review. We figure out the enthalpy for the reaction under standard conditions, get this right out of the table, multiply the value by 2 because we have 2 moles of it. The enthalpies for the nitrogen and hydrogen are 0 because they're in their stable elemental form, and we get minus 92,380 joules for the enthalpy of the formation of ammonia. Now, the entropy of the reaction is going to be products minus reactants, and that's going to equal minus 198.2 joules per Kelvin. And so we can use delta G equals delta H minus T delta S, plug those in, and get the free energy. If the temperature was 25 degrees Celsius, we could determine delta G from the table in the appendix. But since we are at 427 degrees, we have to calculate it from the equation delta G equals delta H minus T delta S. At any rate, you're going to end up with delta G0 equals 46,400 joules, just like we did in the previous question. Now, how do we use that to calculate the equilibrium constant? Delta G0 equals minus RT ln K, because we're talking about equilibrium here. And delta G0 is 46,400 joules equals minus R, which is 8.314 joules per Kelvin, times 700 Kelvin, times the natural log of K. So the natural log of K calculates to be minus 7.97. And we take the anti-ln, the anti-log of minus 7.97, we get 3.45 times 10 to the minus 4. And since K is much less than 1, the equilibrium position favors the reactants. That's because K is much less than 1. And finally, let's talk about the temperature dependence of K. This alludes back to something we talked about in the first equilibrium chapter, that if you have an exothermic reaction, one where heat is being released, increasing the temperature decreases the value of the equilibrium constant. So if you make that system warmer, you push the equilibrium toward the reagent side. And conversely, for an endothermic reaction, one that is absorbing heat, increasing the temperature increases the value of the equilibrium constant and pushes the equilibrium toward the product side. Now, all of this can be quantified in this equation, where the natural log of the equilibrium constant equals minus the ratio of the enthalpy of the reaction divided by R times 1 over the absolute temperature plus the change in entropy of the reaction divided by R. And if you take a good squint at this, you should see that it's in the form of a straight line, y equals mx plus b. So it's a straight line relationship, and it's a very useful one for physical chemists.